Okay, it took a while to get that set up. Let's see here. Yeah. All right, so linear systems and matrices. Systems of linear equations. Definition 1. By a linear system or linear system of equations, we will mean a set of m simultaneous equations in n real variables, x1 to xn, which are of this form. Okay, so a concrete equals 3, that's the number of variables, and m, the number of equations, is 4. All right. Notice here let's see, how would you indicate that? Okay, so that would be, right, okay, so it's that way round. mn. All right, so here, row 4, column 3. In this particular instance, it happens to be 0. And B1 is 5. Okay, I get it. Any vector x1 to xn which satisfies 1.1 is said to be a solution. If the linear system has more than one solutions, it is said to be consistent. The general solution to the system is any description of all the solutions of the system. We will see in due course that such linear systems can have 0, 1, or infinitely many solutions. We will often write the linear system as the augmented matrix, like so. Okay, so I'm going to take that linear system of equations above and present it as an augmented matrix. Five, 6 minus 4, 6 minus 11, 19, and then 1, 1, 0. And then a big bar, and then 5, 4, 3, 8. Just there like that. Okay. For now, we won't consider a matrix such as A or a vector such as B to be anything more than an array of numbers. Consider as a first example the following linear system of 3 equations and 3 variables. All right. Okay, so we have this system. That's the example they've given us. 3x at y take 2z equals negative 2. X at y at z equals 2. And 2x at 4y at z equals 0. So it goes 3, 1, minus 2, 1, 1, 1, 2, 4, 1. And then a bar. And then negative 2, 2, 0, and brackets. So we have to find a solution to this. Okay. Now, they've taken advantage of the fact that the coefficients of the second equation are nice, very nice and palatable. There's 1. So they've said that z is equal to 2 take x take y. And they've used substitution. Picking that up, a rearrangement of this, and placing it in equation 1. And then picking that up and placing it in equation 3. And then you have a linear system of equations which has 2 equations and 2 variables, just like that. The 2 by 2 case, which everyone learns in high school how to solve. Okay, so we should do that. Okay, so what did they say? Right, so they said that x is, did they use x? Maybe they used y. It doesn't really matter. We can use whatever we want. So I like to put 2 in brackets like that to indicate which equation I'm working with. And I'll say that y is equal to 2 take x take z. And then I put it into equation 1. So we have 3x plus 2 take x take z take 2z equals negative 2. And then you rearrange that so that you get an equation in 2 variables. So that's going to be 2x. And then we have minus 3z. And then 2 over there and minus 2 there. So that's equal to negative 4. And then after putting it into 1, we put it into 3. So 2x, add 4, open brackets, 2 take x take z, add z, equals 0. So rearrange that now. So we've got 2x minus 4x, so minus 2x. And then minus 4z plus z, so minus 3z. And then that's equal to minus 8. No. Oh, yes, it is. It's equal to minus 8. Right, so now we have our 2 equations in 2 variables, like that. So we can just say a plus b, and that's equal to negative 6z, which is negative 12. So z is equal to 2. And if z is equal to 2, we put that into a to obtain what x is. So 2x take 6 is negative 4. So that means 2x is 2, so x is equal to 1. Now that you've established that, you can put both of those, the z and the x, into this rearrangement of equation 2 to obtain what y is. So y is equal to 2 minus 2, beg your pardon, 2 minus 1 minus 2. So y is equal to minus 1, or so I believe. And all right, that checks out. Great. Thus, there is a unique solution, 1, negative 1, 2. Yeah, the solution, here it is as a row vector. negative 1, 2. We can verify easily that this is indeed a solution, just to check the system contains no contradictory information elsewhere that we haven't used. Whilst we solved the above case rigorously, we showed of necessity 1, negative 1, 2 was the only possible solution, and then verified that it is a solution. Right, so to verify that it is a solution, you would just simply pick those numbers up and put them in the original equations and check that they yield 3 true propositions. And then the trickier thing is to verify that is to determine that it's the only possible solution. And well, what can be said about that? Well, you can pick any of the variables that you like, and suppose I don't know how you'd prove that it's the only solution. I think that it has to be the only solution because not sure. Our approach was a little ad hoc. At least it's not hard to appreciate that if we were presented with 1,969 equations and 2,021 variables, then we would need a much more methodical while programming our computers to determine any solution for us. We introduced such a process. We first improved the notation, writing the system as an augmented matrix, as I've done there. All that has been lost in this representation are the names of the variables, but these names are unchanging and unimportant in the actual handling of the equations. The advantages we see are that we will be able to progress systematically towards any solution, and at each stage we shall retain all the information that the system contains. Any redundancies, that's superfluous, unnecessary equations, or contradictions will naturally appear as part of the calculation. The process is called row reduction. It relies on 3 types of operation called elementary row operations, EROs, which importantly do not affect the set of solutions of a linear system as we apply them. Okay, so given a linear system of equations, an elementary row operation, or ERO, is an operation of one of the following 3 kinds. The first is that the ordering of 2 equations or rows may be swapped. For example, one might reorder the writing of the equations so that the first equation now appears third, and vice versa. Okay, I've seen that indicated before using capital R for the rows and then giving indices and just, yeah. Let's see. B, an equation may be multiplied by a non-zero scalar. For example, one might replace 2x take y at z equals 3 by x take a half y, add half to that equals 3 over 2 from multiplying both sides of the equation by a half. Right, so that's simple. And then C, a multiple of one equation might be added to a different equation. For example, one might replace the second equation by the second equation plus twice the third equation. And to be honest, or thinking about it, all of these elementary row operations, I mean, it all just comes down to this one. The other two are just special cases of this. If you, if you relax this condition here, that it has to be a different equation, you can just add an equation to itself, and that's a scalar multiplication, isn't it? And then here, to turn A into B and B into A, you could say that from A, we're going to subtract A and then add B. And then for B, we're going to subtract B and then add A. So you see how everything is just a special case of this here, the third ERO. Then they're setting up notation, it appears. So let Sij denote the ERO, which swaps rows I and j, or equivalently the ith and jth equations. I see. Okay, so most people are used to something like this, indicating I want the third row and the seventh row swapped. But over here in these notes, they're using this notation instead to mean swap. And mi lambda denotes multiplying row I by the non-zero lambda. All right, so most people are used to something like this, which means multiply row 11 by 5, but here they're doing it like this. Okay. That's the first two EROs. And now what about the third one, the most important? For different rows I and j, that this okay, that's really strange. So how have I seen this presented before? Let's say you want to add to row 5, you want to add 3 lots of row 2. That's how I would usually see it. But here, they're using A. They're, what are they doing? They're saying, okay, I'm going to grab row 2, I'm going to multiply it by 3, and then add it to row 5. That's how they do it here. Note, this is not standard notation in any way. Oh, brilliant. Okay, but I've introduced it here for convenience. I do not see how it's convenient to be non-standard, but there you go. All these operations may seem uncontroversial. Their validity will be shown in Corollary 40, but it is probably not yet clear that these three simple operations are powerful enough to reduce any linear system to a point where any solution can just be read off. Okay. before treating the general case, we will show how the three equations in 1.1 elementary row get an idea of the process. Okay, so here comes the king of convenience, supposedly. Find all solutions to this. I don't know, I think this was a little bit clearer and a little bit better, but anyway, here you go. Okay, so they're going to swap the first two rows, putting the 1 up there in the top left corner, starting off the main diagonal. I get that. Just swapping rows 1 and 2, no problem. Now subtract 3 times the first row from the second. 3 times the first row from the second, which is like adding -3 lots of the first row to row number 2. And follow this by subtracting twice the first row from the third. Okay, so you've got row 1, yeah? Now multiply the third row by -2 and add it on. Okay. Now what's the point of this? Well, the point of this is to get that entry there to be 0, and then to get that entry there to be 0. Okay, good. So now we've got zeros there. We can now divide the second row by -2. All right. So row number 2, multiply it by -1/2. Okay, gotcha. What's the point? To get a nice 1 right there in this second entry of the main diagonal. Gotcha. We then subtract the second row from the first. Right, so what's generally going on here is, to my understanding, is basically they want a 1 up there, and then once you have a 1 up there, get a bunch of zeros hanging down here, like grapes on a grapevine or something, and then get a 1 here and zeros hanging down like that, and then a 1 here and then zeros hanging down like that, and keep going. And so when do they reach that stage? They reach that stage here. See, 3 1s on the main diagonal and a bunch of zeros here. Then they basically they kind of like go upwards. So they have that, and it's like the next stage is to make your zeros go up. Wait, am I doing that right? Yeah, I think so. Well, that's what it appears to be right now. Okay. In case the systematic nature of the previous example isn't apparent, oh yeah, because it's so obvious, note that the first 3 operations, swap 1, 2, add -3 of row 1 to row 2, and add -2 of row 1 to row 3, were chosen so that the first column became 1 with 3 zeros down in it. Now, what's this little tiny t here? This turns a row into a column and a column into a row. It's called a transpose. I got you. I see. So that was their goal here, to turn that 1, 3, 2 right there in the first column into 1, 0, 0. Okay. There were many other ways to achieve this. For example, we could have begun with multiplying row 1 by a third. Okay. to divide the first row by 3 and then add on -1 of row 2. In other words, subtract row 1 from row 2. And then subtract twice row 1 from row 3 to clear the rest of the column. Once done, we then provided a similar leading entry of 1 in the second row with yeah, okay, so their goal was to get 0, 1, 0 in the second row. Sorry, in the second column, beg your pardon. And then to get 0, 0, 1 in the third column. So is that true? Yes, they did it there. And then they did a bunch of things until they got 0, 1, 0 in the second column. And then they did a bunch of things until they got 0, 0, 1 in the third column. I get you. At which point we could simply read off the solutions, which we found before. We found these guys before. Here are two slightly different examples. The first, where we find that there are infinitely many solutions, whilst in the second example, we see that there are no solutions. 0, 1, and infinity, the big three. All right. First system of linear equations has 4 variables and 3 equations. Okay, so they're doing 2 at a time. And I see which EROs they're doing. But the point is, they've manipulated the system of 3 equations to 2 equations equivalent to the original system. Namely these. The presence of the 0 in the last matrix means that there was some redundancy in the system. Wait a minute, excuse me, hang on. Where's this thing? Are they going to talk about that next? Yeah, okay, they do. Part A. Of course, I didn't see that. Note, for example, that the third equation can be deduced from the first 2. It's the second equation added to twice the first. I see. Yep, you add the second equation to twice the first. And so it gives you, oh, right, so this gives you no new information, as there are now only 2 equations in 4 variables. It's impossible for each column to contain a row's leading entry. All right, so infinitely many solutions. So what do? Just give up? No. You describe the slice of infinity that you're talking about. To describe all the solutions to a consistent system, we assign parameters to the columns / variables without leading entries. In this case, that's, let's say, x3 and x4. Okay, these guys. And we'll assign parameters by setting x3 equal to s and x4 equal to t. And then use the two equations in 1.6. Yeah. Hmm. 1 point, this here makes more apparent that these solutions form a plane in R4, four-dimensional Euclidean space. A plane which passes through that point right there and is parallel to these 2 points right here. Right, so wait, let me think about that. Okay, so I have 2 points floating in space and another point, and the plane passes through that point and it's completely parallel to those 2 floating points. I get it. And S and T parameterize the plane. Okay, in part B, they're going to apply EROs again in a like manner. And wait, what was going on in part B? Still 3 equations and 4 variables. Okay. Okay, so they do the EROs. The EROs, which are totally valid and fine. And and what do they end up with? 0, 0, 0, 0, 1. This here, which is totally impossible. There clearly are no such xi, and so there are no solutions to this equation. Any solution to the system has, in particular, to solve the third equation, and so the system has no solutions. In fact, this was all apparent once the third row had become this. So basically, they could have stopped here. They didn't have to. Wait, what were they doing here? Oh, trying to make that 0. I get it. As the equation it represents is clearly insoluble also. The final 2 EROs was simply done to put the matrix into what is called reduced row echelon form. Okay, so we've seen a linear system can have no, one, or infinitely many solutions. We shall prove this in due course. We finish our example, though, with a linear system that involves a parameter. So, really, we have a family of linear systems, one for each value of that parameter. What EROs may be permissible at a given stage may well depend on the value of the parameter, and so we may see, as below, that such a family can exhibit all 3 of the possible scenarios just described. Oh, cool. That's really interesting. So alpha is this mystery constant. And they're saying, hey, try and find an alpha where the system has one solution, and then try and find an alpha where it has no solutions, and then find one where it has infinitely many. So, okay, so we see that alpha is squared here. So what comes to mind? A quadratic. So what are you thinking? I'm thinking that when it touches the axis, one solution, when it's below, infinitely many, and when it's above, none. But let's just try stuff. Okay. 0, 1, 2, alpha, 3, -9, and -1, negative alpha, alpha, and alpha squared. Okay. So, yeah. What is it that I'm looking for? Wait, let's see. So they're basically just like eliminate those two. All in one step. It's totally fine to do that in one step. What I want you to do is add -2 lots of row 1 to row 2. And then I want you to add row 1 to row 3. At this point, which EROs are permissible depends on the value of A. We would like to divide the second equation by alpha and the third by alpha plus 2. Both of these are permissible provided that A is non-zero, and provided that alpha is non-zero and alpha is not negative 2. Interesting, okay. So when they divide the second row by alpha and the third row by alpha plus 2, they get this. Okay, difference of 2 squares here. And then, now that they have ones on the main diagonal and zeros on the, what can we call it? Name for diagonal half matrix. All right, okay. Now that we have ones on the main diagonal and zeros on the, oh gosh, just forgot it. On the lower triangle. Principal diagonal, upper diagonal. Yeah, okay. So okay, so now in this case here, they've got ones on the main diagonal and zeros in the lower triangle of the matrix. And so they obtain, oh, and zeros in the upper diagonal. Reduced row echelon form, isn't it? Right there. So there are the solutions. We can see that the matrix has a unique solution when alpha is non-zero, or neither 0 nor negative 2. Returning through to the last matrix of 1.9. Okay, the last matrix, which is this one here. Now, if alpha is 0, then you obtain this matrix here. And when you do these EROs, you get this, which has no solutions. When you set alpha as negative 2, you do this, which has infinitely many. Okay, so I wasn't right about it involving, about the way in which it involves a quadratic, but it kind of did. But it's really interesting. That's really, really cool. So for the two solutions of the quadratic, or rather the two variables which would result in division by 0, each of those points to either 0 or infinity. Wow, cool. We see then that the system is inconsistent when alpha is 0 because of the insolvability of the third equation, whilst there are infinitely many solutions in this case here. As long as you set x equal to negative 5 minus t, and y is equal to t minus 1 all over 2, and z is equal to t, all right, when alpha is equal to negative 2. Okay, great. I enjoyed that session. Be well.